The title of this video is Variable Fluid Properties Test Case 2. This is the second of 3 heat transfer cases that we've been looking at and how to set up a heat transfer case in a CFD model. In this particular case, we're going to look at setting up a model that has a specific targeted amount of heat removal, as well as a targeted temperature we want to achieve as the fluid passes through the system. My name is Jeff Franklin. I'm the primary architect of Azore, a commercial CFD package specifically designed to address commercial fluid mechanics problems. If you'd like to know more about this product, please visit the website azorecfd.com. The first thing we want to do is get familiar with the system that we'll be modeling using our CFD tool. In this particular case, we're going to be looking at a system that can be represented using a two-dimensional analysis, meaning that it's kind of an extrusion. Here, you can see the overall schematic of the system that we'll be looking at. And if we start up in the upper left-hand side of this system, you can see that there are 2 fluid inlets here that combine together into a single passageway. And so these 2 streams mix with one another as they progress downward. Then they turn into a tube bundle, and as they pass into the tube bundle, they then return going up, and then they turn again into a second tube bundle and progress downward. And after they pass through the second tube bundle, they then cross out, and then they pass over some flow control devices, some angle irons, and then some flow distribution devices, and then they go around a corner, and then they leave our system. So that's the gist of this overall system. In these analyses that we're going to be looking at right now, we're interested in looking at heat transfer in this problem. And so to help simplify the heat transfer analysis, we're going to assume that there is no energy loss that passes through the walls, the exterior walls of this system. So we're going to assume that the outer walls of this domain are perfectly insulated. The other thing that we're going to assume in this particular test case is that there is no heat transfer through these baffles between each one of the tube banks. And that'll simplify the analysis, the energy analysis between and through these tube bundles. So that's the gist of this flow case that we're interested in modeling. Now we're going to look at some integration planes. Now that we have a good idea of what our system looks like, the next thing we want to do is kind of set up, we're interested in looking at integrated values throughout this system. And I have chosen a number of integration planes, and what we would maybe want to do is get an average value of fluid properties on each one of these integration planes as the fluid mixes and passes through this system. And I've chosen 10 planes, 11 planes really through the system, where they kind of start with plane P1 right here on the left. We have a number of planes right here, and then the P4 kind of represents an integration of fluid properties right as you enter that first tube bundle, and then P5 is as it leaves the first tube bundle and enters the second tube bundle. P6 is when it comes out of the second tube bundle. P7, P8, and then on, and then there's one last integration plane right at the very end of this system. So, and oftentimes, we get CFD simulations allow us to look at some color contours, but we're also interested at times at looking at very precise integrated values, and we want those integrated values to represent, say, for instance, what we would expect from an energy balance standpoint. So these integration planes are going to give us a way of looking at the predictions and what kind of integrated values we might get throughout the system. So we understand the system that we're modeling. We've selected some integration planes to look at the fluid properties as they pass through the system. Now we need to choose some flow conditions. And this slide outlines the flow conditions that we're going to use for setting up our CFD model. And if we look over on the left-hand side, we are going to assume for this lower inlet that we're going to have air coming in with this mass flow rate and this temperature. And then the steam is going to come in at a higher temperature in this upper inlet. So we basically have an air fluid and a steam fluid that are going to be mixing together in this duct. We're going to assume that the flow is turbulent, and we're going to use a two-equation turbulence model to represent the turbulence properties there. And then, so like just to get a rough idea of how tall this system is, it's basically 1.5 meters tall. And then, so this is a heat transfer case. And so for this first tube bundle, we've been told that that tube bundle is going to remove a fixed amount of energy. And basically 150,000 watts or joules per second are going to be removed by this first tube bundle. The second tube bundle, we've been told that they're really expecting the temperature of the fluid leaving it is going to be at a particular temperature of 925 degrees K. That's kind of what they're expecting, and they would like to have us set up our CFD model to achieve that. So for the fluid properties, we're going to assume that all of the fluid properties, the specific heat, the thermal conductivity, density, and laminar viscosity, all of those vary by temperature. But they also are going to vary based on their mixture composition, which means that, like, say, for instance, we have our air and steam that are mixing together. Perhaps at this location, you're going to have that particular area a mixture of both air and steam. And so in those areas, there's going to be some sort of mixture equivalent for what the local specific heat of the fluid as it's represented as a continuum at that particular location. So we're going to use that as well in setting up our CFD simulation. The final thing that we're going to assume is that the pressure right over here is a constant pressure outlet. So that kind of outlines the fluid properties that we're going to be using here, the temperatures, and some of the things that we're going to use to set up the flow conditions for this system. So now we know what the geometry of our system looks like. We know the flow conditions, the operating conditions that we would like to simulate using our CFD tool. The next thing we should do is really do some handbook calculations to kind of get a feel for what we would expect to get out of our CFD simulation. These handbook calculations, I'm going to focus on the energy balance. And to do that, we're going to look at the energy flux coming into our model. And we can figure out the energy flux by looking at both of our inlets. We can start by looking at our water vapor inlet, where we know the mass flow rate and we know its temperature. And once we know its temperature, we can look up, using an enthalpy table method, we can look up what the enthalpy would be of the water vapor at that temperature. And once we know the enthalpy, we can use the mass flow rate. We can multiply these two together, and that gives us the total energy flux due to our water vapor coming into our system. We can do a similar calculation also for our air inlet, and that also allows us to come up with the energy flux of the air. And so now we know the total energy flux coming into this system, and we can add those two together and find out the total amount of energy coming into this system. And once we know the total amount of energy, we can use the total mass flow rate, which is the sum of the air and the water vapor, and we can come up with the total mass flow rate, and we can divide the total mass flow rate into our energy level, and we can come up with a mixture enthalpy. And so this mixture enthalpy level represents the enthalpy of the mixture. And here we kind of have 50% water vapor and 50% air. And we can use that mixture enthalpy to speculate what the temperature should be from an energy balance standpoint here. So in this particular case, the energy level and the mixture enthalpy happen to be the same number, since our total mass flow rate happens to be 1 kilogram per second. So once we know the enthalpy level, we can go up to a graph here and look up, what the enthalpy and the temperature would be. And just to kind of look at this first, we can see right here, the red line kind of represents the enthalpy curve for air. And you can see as the temperature rises, the energy level or the enthalpy rises. And we can also look at the blue line, and this is the enthalpy level for our water vapor or steam. So, but the one that maybe is kind of interesting to us from an energy balance standpoint is what is the mixture enthalpy, and that would be the combination of water vapor and air, 50-50. And so the green line represents the enthalpy level of a mixture of 50% air and water vapor, and you can see that it actually falls kind of halfway between the air and the water vapor, which one would expect. So now we have this nice curve here, and we can use that to kind of calculate what an energy balance representative temperature would be here. And so we would take this number, go up to our graph, look at our enthalpy level here, and just like you would look up like in a steam table or something like that, you would go back over and look right on the green line where this intersects, and then we would go down and we could find out, and we would see that we would expect a temperature somewhere between 800 and 900 degrees Kelvin. And actually, if you do it very precisely, you would come up with a value of 856 degrees Kelvin. So now we really know what the temperature, average temperature from an energy balance standpoint, we should expect before any energy transfer takes place in this system. So now we know roughly what the temperature is going to be coming in there, but we need to set some boundary conditions in our CFD simulation. And we want those boundary conditions to represent some of the assumptions that we would like to make in terms of the heat transfer that's going to occur in our tube banks. And so we knew a little bit of information about what to expect out of that system. And so for the first set of tube banks, we know that the total energy removal there was basically 150,000 joules per second. And we know actually from our previous slide where we calculated the total energy flux coming in, we know what the total energy flux is coming into the system, and we know how much energy we want to remove. And we can actually come up with what the actual energy level should be leaving the first tube bank. We can also look in our model and look at the total surface area of the tubes. And if we want to, for this example, we're just going to assume that the energy is removed uniformly off of each tube. And if so, therefore, if we know the area and the joules per second, we can simply divide our total heat flux and by our area, and we can come up with a basically surface heat flux that we would apply to the tubes. One thing to notice here is basically our energy level, our enthalpy level. Since our mass flow rate is 1, we can see that it's going to go from our 850-ish degree temperature. We're going to go downward down, and we're going to look somewhere in here. So we're going to expect our temperatures to decrease, probably not less than 700 degrees K, but it's going to go down. So, and so for our second tube bundle, it's a little bit trickier there because we have been told that we have a target temperature that we want to have coming out of the second tube bank. And so how can we come up with a boundary condition to put on those tubes to represent that very precisely? And we can do that simply by looking at our enthalpy levels that we would expect. So since we know what the enthalpy level is coming out of the first set of tube banks is right on, we know the energy flux, and since our mass flow rate is 1, we know its enthalpy as well. And so we know the target temperature that we have is 925. And so we can say, okay, well, we know we have a temperature of 925. What should the enthalpy level be when it exits the second tube bank? And we can look that up in our enthalpy table here at 925, and we can go right up here and we can see that it's pretty close to right around here. And so we know that this is the enthalpy level that we're going to look for. And so now we know that the difference between this 700,000 number and this 968,000 number, the difference between those two divided by the surface area should be the amount of energy that we need to add into the system to achieve that temperature. And we can simply do that subtraction here and come up with what boundary condition, since we're going to assume a uniform heat flux on the second set of tubes, and this would be how you would calculate that number very precisely. And then we should get out of our CFD model the exact numbers that we are expecting. So at this point, I think it'd be a good idea to kind of review what the flow structures look like in this system. We'll use the Azore GUI to look at those flow structures and kind of get a feeling for what things look like before we jump into looking at some detailed surface integrals. So here is the Azore GUI, and the model has been brought up. The black lines in this model right here shown on the screen represent basically the hard surfaces in the model. And so to start with, perhaps the first thing we would like to do is look at the path lines in this model, and maybe we'll just look at the path lines starting from the lower inlet. And so this is where our air comes into the model. And so these path lines allow us to see kind of where the air generally is going to be in this model, and you can kind of see it progress through the model, kind of staying on the one side of the duct. We can also look at where the steam is in the model, looking like that. And we look at both. And so the colors of these streamlines are colored by total velocity. So you could kind of see by the color bars here that the higher velocities are from the steam and the lower velocities are of the air. So that's one way of looking at the flow structures. So the streamlines here are relatively straight. They're kind of wiggly as they go through the two banks, understandably. And then we have some flow structures over here as it passes through the flow control devices. So that's one way of looking at the flow structures in here, but another way is to look at filled contours. So let's do that. So to start with, perhaps we'll just look at the velocity field. So here is the velocity field, the total velocity magnitude at all locations within the model. And you can see, just as with our streamlines, the velocities of the steam are higher initially than the velocities of the air. You'll notice over here that the velocity magnitudes become relatively consistent and uniform after it's passed through a number of tubes. You can see over on this side it becomes very stratified as it leaves the tube bank and enters into all of the flow control devices. So the velocity magnitude is interesting to look at, but sometimes it's interesting to just look at the velocity directionality as well. And so we can do that by overlaying velocity vectors onto the solution. And here are kind of a sampling of velocity vectors, and we can change the length of these velocity vectors very quickly to kind of get a look at what the velocity vectors look like and the flow directionality. So over here you can see that the velocity is going downward, but if you look very closely, you'll see right in here that the velocity is actually going up right here. So that's one kind of flow structure that you could look at and get a kind of a general view of what the velocities look like, but sometimes it's interesting to really drill down and look at the velocity structures. And one of the interesting areas of velocity structures is right down in here. And so we might want to look very closely at the velocity structures in this area, and we can use our velocity vectors to do that as well. But we might want to look at, right now they're distributed, not every single cell's velocity vector is shown, but we can ask it to show more velocity vectors by reducing that length scale. And you can see how more and more velocity vectors are shown there. In fact, we can say actually just show them all. And so now we have lots of velocity vectors, but it's kind of hard to see what's going on. So maybe we want to make those velocity vectors a little bit smaller, and we can do that by adjusting their length scale right here, very simply. And so this now allows us to kind of really get a good view of the velocity structure. So we see some eddies forming behind each one of these tube banks, which is kind of interesting to look at. One of the other things that is a little bit interesting in terms of this velocity structure is the flow structures over in this area. So you can see a recirculation zone forming right here, and then you see an eddy forming as it goes through the angle irons. So this is just another way of looking at the velocity structures inside our domain. So the next thing we might want to look at, let's just turn off these velocity vectors for the time, but we can go back to our contours and we can look at many different types of fields in here. For instance, we could look at, say, for instance, the temperature distribution in our flow field. And we see that we have a high temperature of the steam coming in and a low temperature of the air coming in. Another thing that we could look at, say, for instance, are material properties. Here is our specific heat. And so this is the resulting specific heat in each area. So if we were to look over here, this is the specific heat, in terms of those lines that we were looking at. These are the values of the air specific heat. Over here is the lines specific to the water vapor. And right in here is a mixture. So like right in here, say for instance, in this area, we kind of have a mixture of both steam and air. And so this is the specific heat, the mixture specific heat that is, there. So we can not only look at velocity structures, temperature fields, but we can also look at material properties to kind of get a feel for what is controlling the, the predictions of our CFD model. So now that we kind of have a good handle on these flow structures from what our CFD model has predicted. So now we would like to look at some surface integrations of our planes that we kind of outlined at the beginning. And there are a number of different ways you can kind of find an integrated value. And in particular, we're going to look at the different ways that you could find an average temperature value. So we're going to look at 3 different ways of finding an average temperature value on these surfaces. And the first method is going to be an energy conservative way of coming up with a temperature on the surface. And this is an energy balance method. And this is done by kind of looking at the total energy crossing through the plane, and we can find the total energy crossing through our plane by, just like we did when we were looking at our handbook calculations, we kind of get the enthalpy for each facet of our surface, and we multiply it by our mass flow rate, which is the density times the normal velocity times the area. So right here, we can kind of find, just like we did with our handbook calculations, the enthalpy flow rate, an energy flow rate as the mass passes through our surface. But in general, for our CFD calculations, there's also another mode of heat transfer that occurs through a surface, and that's via conduction. And so we can characterize that heat flux by looking at the temperature gradient across our surface. So this term right here is the delta T normal to the surface. And then we multiply it by the thermal conductivity, and this would be the effective thermal conductivity due to turbulence. And if you look at the previous videos that I have on what the effective thermal conductivity is, I'll have a link to that in this YouTube video. You can get an idea of what that really means. So anyway, we have these 2 values that characterizes the total energy passing through our surface. And once we know the total energy passing through the surface, we can divide that total energy flux by our total mass flow rate passing through that surface, which is this denominator right here. And when we divide those 2 together, we get a mixture average enthalpy value. And just like we did with our handbook calculations, we could essentially calculate what would be the representative temperature of that mixture enthalpy. And here we would use that right here to find an average temperature. And so this would be a temperature that is representative of an energy balance, one that we would expect to get from a handbook calculation, and really what we would expect to get out of those. So the next method I have kind of outlined here is a mass flow rated method here, where we take the temperature at each location, each surface facet, and we multiply it by the mass flow rate passing through that single facet, and we sum all of those up, and then we normalize that value by the total mass flow passing through that surface, and then we get yet another representative value of the average temperature on that surface. So that's another way of finding an average value on a surface. Yet another method would be to find an area-weighted average. And here we would take the temperature on each one of the facets of our surface, multiply by the surface facet area, and then divide by the total area. And that will give us yet another average temperature value. So we're going to use these three different methods to find the average values of temperature for our system at the different integration planes that we have set initially in this model setup. So now we have the surface integration techniques that we want to look at. Let's now look at our flow field and see what kind of values we would get there. So let's first look over here and remind ourselves of the geometry. So we have a number of different planes. This is the temperature field shown here. And so plane 1 would be this plane right here. And plane 2 would be the next one in, and so on and so forth. So we can look at the average temperature on each one of these planes and look and see how things change. And we would kind of expect it to change based on what was happening. So like, say for instance, the average value of these three right here should be kind of an average temperature that we got from our energy balance. And then we would expect the temperature to drop as it goes through the first tube bank. And then we would expect it to go up as it goes through the second tube bank and then remain constant as it goes through here. That's kind of what we would expect intuitively from our engineering perspective, but we're going to look and see what kind of values we would get from our different averaging methods. And this line graph over here shows those different predictions. And so the red lines represent where our enthalpy or energy conservative based method of calculating average temperature values. The blue line represents the mass weighted average. And then the area weighted is shown based on the green lines. And you can look and see, and it's very noticeable that you get very different values. And that is the important aspect of understanding when you're getting an average value, what does it represent? Do you want an energy conservative value, or do you want another value because of other reasons? And say, for instance, you were looking and you might say, well, this value right here doesn't really represent the energy conservative value from an area weighted standpoint, but perhaps you would like to compare your simulation predictions to, say, for instance, if someone had a rake of thermocouples along plane 1, and they gave you an average temperature that was based on those thermocouple readings that are area weighted average temperature. So then this would be the number that you would maybe want to compare to those values. So it really depends on how you would like to interpret those averaging values and understand the difference between values that might be energy conservative and values that represent some other method of measurement. So say for instance, they were measuring the velocity profile, and so they did a mass weighted average, then perhaps you would want to use it here. But if you really truly want energy conservative values, you would need to use this energy conservative method that is offered by Azore. So just also, I'm going to show you here, these are the hard numbers, so you could kind of look at what's happening here. And this is exactly what you would expect. So for the energy conservative method, you see that the numbers remain precisely the mixed value that we had calculated previously with our handbook calculation. And then you can see here that there's a drop in temperature through the first tube bank from an energy conservative standpoint, and then a raise in temperature here that is the target, close to the very target temperature that we asked for. So our boundary conditions gave us what we expected from an energy conservative standpoint, but these other methods report different values, and they are noticeably different. So in summary, we've looked at a number of different things. The first thing we did, we looked at the geometry of our test case. We looked at the flow conditions that we wanted to mimic using our CFD tool. And then we also outlined a bunch of different integration planes where we wanted to extract detailed information about the flow structures and in particular the temperatures at different planes throughout our system. We looked at how we set up our two banks. In this particular case, we were interested in removing a certain amount of energy, and we looked at ways of figuring out how to set our boundary conditions for that. And then we also looked at ways of, in the second two bank, about how to add energy in to drive our fluid temperature to a particular specific temperature that we have been told is what that system does. And then we looked at a number of different surface integration methods. We looked at an energy conservative surface integration technique. We looked at a mass weighted temperature as well as an area weighted temperature, and we reviewed what the differences we observed in this particular test case. So this concludes all of the technical content for this video. If you're interested in other videos similar to this one, please visit the Azore YouTube channel at Azore CFD. If you're interested in more technical content and if you would like to learn more about Azore, a very powerful commercial CFD package specifically designed to solve industrial systems, please visit the website azorecfd.com.